So yesterday I gave you a discrete model that we're looking at to try to think of the limit of, actually a couple of discrete models. Today we're going to be essentially all continuous, trying to find a continuous model that satisfies this. So the two ingredients are conformal invariance and domain Markov property. The first thing I'm going to be discussing at this is the fundamental work which was done by Oded Schramm, who died tragically a few years ago at a high cancer, but for whom this process is named. So, roughly speaking, he was looking at possible measures on paths using the notation I had yesterday. I'll call this mu sharp dzw. The sharp indicates that I'm doing a probability measure. In this case, a probability measure on paths from z to w in d. Right now, we'll think of those being simple paths, non-intersecting paths. Conformal invariance means that if I map by a conformal transformation, I get this. So now I'm talking about curves. When I talk about a curve, it's a continuous image of, say, 0, 1 or 0a for some a. But for the time being, we're really going to think of curves modulo reparameterization. We're interested on where the curve goes, but not so worried about the speed that it goes. So when I take this conformal transformation, I'm saying that this should be invariant, at least in terms of what points one goes to, and not worrying about the parameterization. We'll discuss the parameterization more as we go along. So that one's conformal invariance. And the domain Markov property, I talked about it yesterday, but I'll draw it in a picture here. Suppose I'm interested in this measure, and I see some initial segment, which I'll call gamma, and I'm interested in the distribution of the remainder given that. So in this measure, distribution of, and I'll just take advantage of colored chalk, of the red part, the distribution of the red part given the white part I called gamma over there, is, well, just call that gamma t, that endpoint, just giving it a name. The distribution is given by, I take d, take away the gamma, the split domain, from gamma t to w. So given what I have so far, the remainder is this process in this slit domain. And so the question that Oded asked is basically, given conformal invariance and the domain Markov property, what kind of processes can you get? And the first thing he did was he restricted to simply connected D. And we'll stay with simply connected D for most, if not all, of this talk. And for simply connected D, we have the Remonte mapping theorem. that basically states any two simply connected domains which are strict subsets of C. Don't count C itself. Any two things that are strictly contained in C are conformally equivalent. Moreover, I can find, if I make this point Z prime and this point W prime, I can find a conformal transformation that sends Z to Z prime and W to W prime. There's actually one parameter family of these things, and when we get to a particular example, we'll get to this. But the first thing you get from this fact is that if you're just dealing with simply connected domains D, and you have conformal invariance, then in order to define the family of measures, we only have to define it on one simply connected domain. And what he chose was the upper half plane. And the boundary points to be 0 and infinity. So now we're going to assume we have a probability measure on curves from 0 to infinity in H. So let me draw. There's 0. I won't draw infinity. And here's a curve. Let me draw. That's going to be the start of it. It'll keep on going, but let me just use a different color for the continuation, just to. Let me call this time gamma t, just to. So for any fixed time t, I have the domain, which I'll call ht, which is h minus gamma 0t, the slit domain. Actually, maybe for the time being, let me get rid of this. Right now, we're really focusing on this right here. And what we're going to do is map this domain back to the upper half plane. Now there's a number of conformal transformations that take the half plane minus the slit to the upper half plane. To make this specific which one we're talking about, we're going to first assume that I send infinity to infinity. We don't see infinities being sent to infinity. And we're also going to assume that at infinity, the derivative looks like 1. So in other words, my expansion at infinity, as z goes to infinity, gt of z looks like, well, the first term is z. That's combining these two facts. Now, I've yet to specify this map precisely, because it takes 3 real degrees of freedom to specify the map. So the next term here is going to be a real translation. And I can choose any real translation. I'm going to choose this real translation to be 0. And therefore, I'm not even going to bother to write it. So plus 0. And now I've actually specified my map precisely. There's a unique map that sends gt of infinity to infinity, gt prime infinity to be 1, and that the real coefficient here is 0. And its next term looks like this. And I'll just write the coefficient as that. That depends on t and the curve gamma. So it's a of t is now, as it turns out, it's not too hard to show that a of t here is a kind of capacity. The important facts are that a of t is continuous and strictly increasing. At least in my book, we actually, it's called the half-plane capacity of this thing. And this discussion, okay. But right now, that's all that we need to know for right now. And the basic idea, which was an idea used by Loewner in complex variables in the first half of the 20th century, and either adapted or reinvented by Schramm. I'm not exactly sure of the history of this. But the idea here is that to make life easy, we reparameterize so that a of t is smooth. And in fact, since we're bothering to do that, we might as well make it linear. So we reparameterize gamma so that a of t is linear, and a lot of, for various reasons, 2 was the factor chosen, but that's an arbitrary choice. So that's just defining g sub t, but once I define this, if I start with a point z in the upper half plane, it moves to a point that I'll call gt of z. So for fixed z, we now have a function of t, which is z maps to gt of z. And the theorem is that for z in the upper half plane, gt of z satisfies the partial derivative with respect to t of this is 2 over gt of z minus ut. And now I'm going to take my picture up here. I'm going to call that point u sub t, where u sub t is the image of gamma t. This is not immediate, but it's not a very it's a deterministic fact. But it's actually, when you to think about this, is actually sometimes useful to think probabilistically. Let's look at this at t equals 0. Let's just look at a t equals 0. Maybe I'll draw over here. At t equals 0, there's z. And now I'm drawing a little curve here. And I'm interested, how does it affect the image of z? Well, I'll just say holomorphic harmonic functions and more general holomorphic functions can be written in terms of Brownian motion. the effect on Z is basically based on the probability a Brownian motion from Z hits that point. It's basically no potential theory. And this quantity is what's called the complex form of the Poisson kernel. Sometimes there are other names for it as well. But the imaginary part in particular is actually the Poisson kernel, which is the probability basically that the Brownian motion hits there before it hits there. So I'm just saying this. So it's not a magical fact, but I don't have time to do everything today. So, but an important fact, this is just a deterministic fact. All I've done right now is assume I have a simple curve. One other fact that in this case is that t goes to ut is continuous. This equation makes perfect sense as long as z is off the curve. It makes perfect sense. If z is on the curve, then it blows up when the curve actually hits z. Okay, so that's the differential equation. Maybe I didn't write the name Loewner up. I should. So now let's go back and assume I have a random curve, a measure on curves. If I have a random measure on curves, that gives me random g sub t. That gives me random u sub t. And if I have random u sub t, conformal invariance and domain Markov property imply that if s is less than t, then ut minus us is independent of everything that's happened so far. U sub r minus u sub r less than or equal to s, with same distribution as ut minus s. And the deterministic fact tells us that it's continuous. And so what Schramm observed was that if you have something satisfying those two conditions, then in fact u sub t must satisfy this. And it's a theorem in probability that any process with continuous paths and independent stationary increments must be Brownian motion. Now if I take so it's a one-dimensional Brownian motion. U sub t is a one-dimensional thing. A Brownian motion is specified by two parameters, a drift parameter. Now a drift parameter would move it around this way. There are many ways to find that in fact the drift has to be 0. There are a couple of different ways of doing it, but just so drift 0. There's also a variance parameter, and that is important. And Schramm labeled that variance parameter as kappa. So let me now make a definition. So definition, the Schramm-Loewner evolution by the way, Schramm originally called this the stochastic Loewner evolution. And I'll put a cap in there. From 0 to infinity in H is the path obtained by solving the Loewner equation. I'm just going to call it, give it a star. With UT being a Brownian motion with variance parameter kappa, well, I'm going to write that as square root kappa times the standard Brownian motion. Now, there's a little bit of theorem hidden in this definition. If I stick a continuous function in here, like a Brownian motion, there's no problem showing that for each z, the solution of this is defined for a while. But it's not necessarily true just for general continuous guy that you have a path there. But this is a theorem mostly proved by Rohde and Schramm, one particular harder case done later. But I'll just say that there exists such a curve. Now, if you've never seen this before, this is actually a very hard way of describing a process. We're trying to describe a curve. And in order to describe the curve, we describe the non-curve. The G sub t is telling you what's happening off the curve. The curve is where things are bad. So it's a tricky way of doing this, defining it. But it does it. If you've seen pictures of Brownian motion, one-dimensional Brownian motion, if you do this is Brownian motion. If I change the variance, I do this, or this, it still looks the same. For here, the amazing thing is that the qualitative behavior of gamma changes drastically as you change kappa. So let me first state some of the facts about this, then I will discuss a little bit about the proofs, at least some of the proofs. Before I do that, I'm just going to change this formula slightly. So, okay, I didn't change. Okay, that's what we're dealing with there. This is parameterized so that you always have a 2 there. I personally hate having square root kappas multiply my Brownian motion. So I will reparameterize. I'll make a slightly different parameterization. I'm going to let A be 2 over kappa. And I'm going to look at this equation. So here, this will be a standard Brownian motion. And what I've done is, instead of growing so A of t grows at rate 2, A of t grows at rate A, which is 2 over kappa. And this is an alternative definition of SLE kappa, where kappa and A are related by that. Okay. So phases. If 0 is less than kappa, less than or equal to 4, gamma is a simple curve. So I'll just draw a little, so think of this as being the picture. If 4 is less than kappa is less than 8, gamma has self-intersections but does not cross. This is a little tricky to draw, but think like this. This is actually happening at all scales. But think of something like that happening. But what's happening here is that there are actually parts of the upper half plane that are not hit, but they get trapped. So that this map G sub t actually has domain equal to that. And if kappa is bigger than or equal to 8, gamma is plane filling. Meaning it's still not crossing, but it hits every point. Now this is very hard to draw. Okay. How do you draw a plane filling curve? Like, it has to be like this. I'll draw the image at time. The image at some time looks like this. The image is always filled in, and my current position is on the boundary. So that's the image at one time. So how do you show something like this? Let me do the first one. Let me do the simple versus not simple. So I'll try to do this case. Let's suppose for a minute that my curve had a self-intersection. I'm just going to change color here for convenience. So there's a curve with a self-intersection. Let's look at this time right here. And let's look at G sub t. So G sub t is just removing the blue part. So the green hasn't been seen yet. So G sub t does this, and that point goes someplace. And then this curve, conformally mapped over there, looks kind of like that. So what I see is that if I have a self-intersection, then at a different time, I actually have a curve that hits the real line. So an equivalent question is, does gamma hit the real line after time 0? So we're going to try to ask that question, and now we'll draw it again. So there's my curve. Let me just choose a point. 1's just an arbitrary point. And let's ask the question, do I hit 1 infinity. Maybe red's a better color. So do I do this? Well, let's draw this picture right before it hits. So there's right before it hits. So now that's time t. And let's map by gt. Let's see what happens here. Okay, as I go along here, there's hardly any room here. So from infinity, it actually really doesn't see the inside of this curve. It barely does, hardly sees it. So when I do this conformal map, this u sub t ends up being around here. It's almost at the end point of that line. And gt of 1 is just barely there. And what happens is, as this curve hits here, these 2 points get together. So another way of asking this, does gt of 1 minus ut reach 0? So what I've done is I've just taken this geometric question and tried to change it to something about the process. But now let's look at this equation. We're going to stick z equals 1 in this equation. And let's let zt be gt of 1 minus u sub t. Which is the same thing as minus b sub t. Then dzt equals a over zt dt minus a standard Brownian motion. That's the second term that's missing there. So minus a Brownian motion and plus a Brownian motion are the same thing in distribution. So now we reduce to a one-dimensional SDE, and this is what's called a Bessel equation. Related to the Bessel differential equation. And it's a well-known fact, which I won't prove here, good exercise in stochastic calculus, that this hits 0 if and only if a is less than a half. If a is bigger than a half, then the repulsion to 0 is sufficiently good. And a less than a half is the same as kappa bigger than 4. And that's basically the proof of this. For this, it takes a little more work, but I want to actually focus on this a little bit and try to discuss a little more while I'm at it. So what I'm going to do is I'm going to take my SLE and ask the question, let's take a point z in the upper half plane how close does it get to Z? How close does the path get to Z? Now, while I'm doing this, let's do a back of the envelope calculation. We're actually going to work out the fractal dimension of the curve. By the way, when I use the word fractal dimension, I'm hedging my bets as to exactly which specific dimension I mean, whether I mean Hausdorff dimension or some other kinds. Is that a question back there?
Yeah, I was just wondering, in this case where kappa is between 4 and 8, you said that it comes around and it sort of touches the curve again.
Right.
And then it divides the plane into different pieces.
Right, and that's what I tried to explain. Then the map G sub t is just a conformal transformation of the unbounded component. That's what it turns out to be. I didn't prove that.
Okay.
So so all those points that got trapped, actually the differential equation is blown up there too. Yeah, so if it's not a simple curve, it turns out the equation blows up at points that are not on. Thanks.
Thank you.
So if I'm doing the fractal dimension of a set, the first back of the envelope calculation is to cover the set with balls of radius epsilon and try to figure out how many you need. So you need epsilon to the minus d balls of radius epsilon. Let's just put the set in a compact set. So if it takes epsilon to the minus, just roughly speaking. So the fractal dimension d satisfies something like that. Or in 2 dimensions, we could think of it as the probability to hit a particular ball of radius epsilon should look like, well, there are actually epsilon to the minus 2 such balls. So this should be epsilon to the 2 minus d. This d is that d, and this 2 is because we're in 2-dimensional space. We're living in the plane. So I'm using d for this fractal dimension. I'm saying that because actually I want to do the calculation. Think of this as being a small epsilon, but if I make it too small, you can't see in the back. So there's a ball of radius epsilon about z. And now my question is, does my SLE hit there? You may note both in this picture and that picture, I'm trying to find something out about the curve. But again, I'm looking off the curve. Here I was looking at 1 in order to try to figure out what was happening at the curve. Here I'm going to look at z to try to figure out what's happening on the curve. But I'm really looking off the curve. So the question is, am I going to hit here? Well, let's look at this. Suppose I've seen a little piece of the curve. And now I ask the question, given that little piece, what's the chance I hit that? Well, this is gamma t. We'll go by gt. So that's now gt of z. This is ut. And now, remember, epsilon is small. even though it's not small in this picture. Think about it as being small. If this is a ball of radius epsilon here, it's being mapped approximately the ball of radius gt prime of z epsilon. There's a derivative factor there. So now, the probability of hitting a particular ball, let's assume for the moment we had a D, which looked like this. There should also be a coefficient here, and you would expect the coefficient might depend on the point Z. So suppose that probability, as epsilon goes to 0, is absolute some function of Z times epsilon to the 2 minus D. Now, over here, we get g of gt of z minus u sub t, gt prime of z to the 2 minus d times epsilon to the 2 minus d. That's the conditioning. And as long as I average over a small little curve here that's not going to reach that far, the average of the conditioning should be the original thing. That's just a martingale property. It would be more precise to say local martingale, but that has to do with when you get close to the curve. But basically, what you end up seeing is that m sub t equals gt of z minus u sub t times gt prime of z to the 2 minus d must be a local martingale. If you don't know what a local martingale is, but you know what a martingale is, just think martingale for the time being. So this is a geometric, we look at it geometrically and we work out this fact has to be true. And now going back again to this paper of Rohde Schramm, that basically you say, well, I know the stochastic differential equation for this. I need something to be a local martingale. If I assume life is good and that G is differentiable, I can use Ito's formula to give me a differential equation for this. I'm not going to do the calculation, though it's actually fairly routine. But the answer is, if kappa is less than 8, then the only way you can get a solution to this is d equal to 1 plus kappa over 8. You also find out what g of z. I'll just write down the formula since I'm here. G of z is equal to the argument of the sine of the argument raised to the 8 over kappa minus 1, if you're interested in what it is. It's maybe, okay, this determines things up to a multiplicative constant. So you might multiply the constant. So. And as it turns out, what we've done is actually compute the dimension of the path. Now it takes more work to do Hausdorff dimension. Vincent-Boffard is the first one who actually did this 2-point estimate to get it. So I'll just write this as a theorem. if kappa is less than 8, the Hausdorff dimension of SLE kappa paths is 1 plus kappa over 8. In particular, for every number d strictly between 1 and 2, there exists a unique kappa which gives you paths of that dimension. So you can actually, all the SLEs are given by fractal dimension, are fractals, that's their Hausdorff dimensions bigger than one of the paths. Once it gets up to 8, then it's space filling, plane filling, and its dimensions 2, but below that's equal to that. Okay, but now a big question is, which kappa for which process? And for that, we're going to do some more calculation, or parts of calculation. Well, first thing, I didn't say it explicitly. I defined SLE kappa from 0 to infinity in the upper half plane in terms of the differential equation. Now, one of the assumptions was that SLE is conformally invariant. How do I define SLE in other domains, simply connected domains? I just define it to be the conformal image of what I had from 0 to infinity. So mu sharp, mu d sharp, zw, if d is simply connected, z and w are boundary points, is just the image under the conformal transformation of SLE in the upper half plane. So that leads to the following question. And this is a picture I've drawn a lot. In fact, I've drawn a lot. I think I'm going to go over here instead. The top board's easier to see. So let's start with the upper half plane. And now I'm going to take a subdomain of the upper half plane. So for ease, we'll just make this 0. And here I'm going to cut out a piece of it. So I'll call this set K, and D is H minus K. Now I'm doing SLE from 0 to infinity. And I can do it from 0 to infinity in H or in D. And the question is, how does the distribution change of this path if I think about it as being in H versus being in D? Let me cut off a piece of this. So let me show you how one does this. Well, first, ignore the SLE curve for a moment. Let's just look at this guy. There's a conformal transformation phi. Maybe I'll write over here. Phi takes H minus K to H. And it's still, and it sends infinity to infinity and derivative 1 at infinity. Turns out it doesn't make much difference. Well, I'll also send 0 to 0. Doesn't make much difference. And I'm just going to, okay. So one way to get the measure on SLE in the smaller domain is to take SLE in this domain and map it, in this case, by phi inverse. Well, there's another way of looking at this. Let me actually ignore this for the moment and just use the Loewner equation to get rid of this. That gets mapped somewhere. That's just where it gets mapped. But this is just the Loewner equation. I'll just call it G sub t. And now here we're actually going to have, I guess, commuting pictures if you use algebraic terminology. We can either go this way and remove this, or we can go this way and remove this. So I'm just and I'm going to give a name for this. I'm just going to call it phi t. So I'm not going to do the calculations. I just want to give you a hint of what you can do here. Is that what you do is we start, if this is a Brownian motion, then we could look at this. I'll just give this a name. Ut is ft of ut star. So and we can use Ito's formula to determine the distribution of u sub t. It's not something you want to do in public because there's a little bit, you have to be a little careful with your Loewner equation here. But and what you get is the following. So I'll call it a theorem. SLE kappa in D, assuming D is of that form, is the solution to the Loewner equation. Let me rewrite the Loewner equation. Where ut satisfies, well, if D were just the upper half plane, ut would be a Brownian motion. But here, ut has a drift that keeps it away from here. And so dut equals, turns out to be, take log phi t prime of ut prime. So when I'm writing this, this is shorthand for phi t double prime over phi t prime. Log of phi t prime prime. And then there's a parameter that comes in. Actually, I should use some other letter. Where WT is a standard Brownian motion. Thank you. Now, I've actually done a little more besides Vito's formula. I've also changed parameterization here a little bit because there's a capacity parameterization here, a capacity parameterization there. It's a lot of calculation, and I'm not going to do calculus in public. By the way, I put a parameter there in, but it may be one you remember from yesterday. It is going to, but in this case, B turns out to be 6 minus kappa over 2 kappa. And that's the first calculation of an exponent, a term, in terms of SLE. So it's just calculation. It's all rigorous on the SLE level. Now, one particular value of interest is kappa equals 6. That's where B is equal to 0. For kappa equals 6, and for only kappa equals 6, if you looked at this curve, and you saw the distribution of this curve, and it's just over here, you couldn't tell whether or not that guy was there or not. And this property is called locality. Now, kappa equals 6 happens to be one of the curves that actually has intersections, and I'll just say that this is the interface for the percolation exploration process. And Smirnov proved that the exploration process actually converges to kappa equals 6. But this is an example. I'll just say, I won't define this now, but if you did this discretely, you would see that this thing would have to satisfy locality. And this is the only kappa that satisfies locality. Okay, now I want to continue this picture. I have these things. Now I'm going to define another quantity. I think everything is there. Let me define m sub t to be equal to phi t prime of ut raised to the b e, and now we're going to have to remember some things from yesterday. E to the c over 2. Actually, I have to tell you something about today too, okay? C over 2, lambda h gamma t k. So I'll explain all these things as we go through. Okay. So this is gamma t. Think of just gamma t as being the image. Gamma t is gamma 0 t. This is the Brownian loop measure of loops that hit both k and gamma t. Brownian loop measure of loops in H that hit both gamma t and k. And C is a number and that number turns out to be 3 kappa minus 8 times b. Okay, I still haven't told you the main fact. Okay, I also want to write this as 6. I'll say kappa, 6 minus kappa, 3 kappa minus 8. Over 2 kappa. And, okay, right now I've just written that. The fact is my notation is good. My notation is good means I used capital M. I used capital M when I want martingales. So the fact is, M sub t is in this case, we should just say local martingale. So for our purposes, for local martingale, we can think when we do Ito's formula, there's no dt term. The dt term disappears. And for a particular value of kappa, that's the only combination where this works. Now I want to make more of a statement over here, and then I'll start doing some consequences. So for the moment, okay, I'm hiding what was down there, and that's fine. We don't want to see it at the moment. So what we've done here, we've just started with a Brownian motion. Well, Brownian motion, a standard SLE. That's what we have here. We happen to have a set here. Because we have a set here, we can define all these maps. At least if this curve hasn't hit this. And that's the statement that I mean. If I start with just usual SLE in this domain, define these maps this way, then this quantity turns out to be a local martingale. Now, an important thing about local martingales, well, martingales, and then you can do it for local martingales as well, for positive martingales, is the Gersonov theorem. So the Gersonov theorem in stochastic analysis basically says if you've got a positive martingale, you can use the martingale to give a new probability measure. And that's called tilting or weighting by the martingale. You can do the same thing for a local martingale as long as you stop the local martingale before something bad happens. In this picture, we can't let the path hit here. We let the path hit here. If I do Gersonov, when I weight by a martingale, with respect to, if I start with Brownian motion, then I end up with a process which is absolutely continuous with respect to the Brownian motion. It attains a drift term. And you can get the drift term based on what you get from this equation. And the theorem is that when one weights, or in other words, tilts by the local martingale, then one gets a new thing. The calculation one gets is exactly this equation. That's what you get. Or in other words, if I start with this martingale, local martingale, and weight by it, the weighted tilted measure is exactly Brownian motion in the smaller domain. In other words, one gets SLE, let's say, in smaller domain. So there are three different ways, at least locally, to describe SLE in smaller domains. One is by conformal transformation. The second is by solving the Loewner equation, and there's the drift that you get. And the third way is to write down this local martingale and then tilt by that local martingale. Well, I shouldn't write. No, I'm not ready to write this yet. Sorry about that. Okay. The next theorem, or the next, I'll just call it a fact, is that if kappa is less than or equal to 4, we can actually let t go to infinity. So I've got this martingale. So I'm starting with SLE up here. I'm tilting by the martingale. I'm weighting by the martingale. When I weight by the martingale, I get SLE in the smaller domain. SLE in the smaller domain for kappa less than or equal to 4 does not hit here. Therefore, in the tilted measure, in the weighted measure, this thing actually goes to infinity without something bad happening. And so this next statement is for kappa less than or equal to 4, and we can actually write, I'm going to write, I can define a process which I'll call d mu d 0 infinity. So I'm going to define, this is actually not going to be a probability measure. This is a probability measure. I'm choosing this to be, whether I put a shot, I'm just choosing this to have norm 1. And I'm going to choose this measure by giving its Radon-Nikodym derivative with respect to this. And what you get is what you get if you plug in t equals infinity up here. It's a little bit of an exercise you can play around. As t goes to infinity, this term actually goes to 1. That term goes to what it goes to at t equals infinity, which is exp c over 2 lambda h, the entire path, and k. But yeah.
If kappa is less than 4, then this part of the yield is just uniformly integrable, yeah?
It's uniformly integrable. And the way to justify the uniform integrability is by saying that when I weight by that martingale, life is good. Nothing blows up. It's not true for kappa bigger than 4. So that's the main calculations that are needed. And now the rest that I'm going to say really just follows from that. So I'll do kappa less than or equal, I'll restrict to kappa less than or equal to 4. So let's look at mu d zw, where d is simply connected and z and w are in the boundary of d. And for the time being, let's assume that the boundary is smooth near those points. Then I will define SLE from z to w in d to be equal to a total mass. This is just a number, which I'll say in a second, times a probability measure. So that's okay. This is just a tautology. This is just the total mass of this measure. But I can actually say what it's going to be. So CD of ZW is the, well, boundary Poisson kernel. I'll explain in a second what I mean by that. Raised to the bth power. What do I mean by boundary Poisson kernel? Well, the Poisson kernel is a measure on paths from there to, or it's the density of hitting W from there. It's the derivative of this as I go to Z. Or you can also think of this as being the derivative of the Green's function, differentiated in both variables. Or if you don't like that, I'll just define it to be, we'll call this H. This is a boundary Poisson kernel. In the upper half plane, it's 1 over x squared. And then it just maps by conformal covariance. But this factor b comes in, this boundary scaling exponent. And then this is the conformal image of Schramm's SLE. And if I define it that way, then I get the properties conformal covariance and what I sometimes call boundary perturbation, or sometimes called generalized restriction. If there's D, and suppose D prime is a subdomain of D. So suppose D prime is contained in D. But I've cut away from Z and W. Then D mu D prime ZW over d mu d zw of gamma is equal to e to the c over 2 Brownian loop measure in D of loops. This is a curve gamma that hit both gamma and d minus d prime. And now we return to yesterday's lecture, where we were defining this lambda self-avoiding walk where lambda is equal to minus c over 2, suppose I took the limits as I had in there, and I took a very fine lattice here and looked at SLE in D versus D prime. So probably should have written, yeah. Well, when I changed the domain, I changed the measure by the number of loops that hit there. And in this case, it would be random walk loops that are in D but not in D prime. But in the limit, that's the macroscopic Brownian loops. And so that's why we would expect that if lambda is equal to minus c over 2, then we actually get this process. Now, if lambda is equal to c over 2. Now, a few comments that I didn't make before. I'm going to put this formula up again. Slightly harder than yesterday's exercises, but not much harder, is that that if kappa is in 0, 4, it's in one-to-one correspondence to c in minus infinity to 1. Kappa equals 4 gives you c equals 1. Another exercise, which is easy, is c of kappa is the same as c of 16 over kappa. When kappa is bigger than 4, I can plug into this central charge formula, and in fact, I get these. And there are various things, actually. There's a whole theory of duality, which I don't have to talk about. I'll just mention it because it's so beautiful. If I take kappa bigger than 4, this is a process which hits itself. I can actually look at the outer boundary of it. Look at the outer boundary. And the outer boundary of 16 over kappa is kappa. So SLE with 16 over kappa is related to SLE over kappa by this PUG. There are various forms of this proved by Jean and Dubé-Da, and I won't go into that. I don't have much time left, and I do want to put some values up here.
You say that the boundary of this process is SLE curve?
It's locally like an SLE curve. I could be precise about it, but that would take me more time than I want. But locally, the outer boundary of an SLE 16 over kappa is like an SLE kappa. I mean, a quick rigorous statement would be the dimension of the 16 of the outer boundary of 16 over kappa is 1 plus kappa over 8. So let's return to the self-avoiding walk. Maybe this is, I don't have much more time than for this. Since I discussed the self-avoiding walk, yesterday. For the self-avoiding walk, if you remember, we had domain Markov property, conformal covariance, and the restriction property. Well, domain Markov, conformal covariance, and the restriction property, and I want something that lies on simple curves. what I've now shown is that there is only one possibility for the limit. Only one possible limit. Again, I should emphasize that means if all these things, if it does have a limit with these properties, there's only one possibility. And if you check in here, it's kappa equals 8/3. And I'll let you, these exercises, B equals, well, C is equal to 0 is the restriction property. B is equal to 5/8. By the way, yesterday I gave you boundary to boundary. I also discussed interior exponents. I don't have much time to discuss this, but I'll say there's still something called radial SLE. But you can actually work out what in general, the interior exponent, what I called B tilde yesterday, turns out to be kappa minus 2/4 times B. And for SLE, 8/3 is equal to this. Now on Friday, I'm going to discuss a little bit about self-avoiding walks. I'm going to discuss critical exponents for self-avoiding walks. And they're not actually, won't be defined exactly this way, but, oh, they're actually, so there's also, while I'm at it, fractal dimension is 4/3. All of the exponents you can get for self-avoiding walk, if we make these assumptions, will be able to be computed from these numbers. And, thank goodness, computer simulations very much agree with these things. Okay, so that's the man. Just since I'm here, I will have 2 seconds more. I'll just list some other values of kappa that you may have seen. Kappa equals 2 is loop erased walk. If you think of loop erased walk I think it's a measure obtained by taking simple random walks and erasing the loops. If I cut off a piece of the domain, then a particular loop erase walk is less likely to be done. Because basically, if I cut off part of the domain, there are fewer simple random walks that can produce this. So, translated here, that would say that for loop erase walk, you would expect C to be negative. When I shrink the domain, the intrinsic measure of a path decreases. And it turns out, and if you check, well, that's C equals -2. And this is actually a theorem. Actually, everything I'm going to put on this board is a theorem. Cap equals 3 Ising interface. Interface between plus and minus. Stas Smirnov and then plus a number of his collaborators have various generalizations of this. Cap equals 4 Gaussian free field interface. And that's Oded Schramm with Scott Sheffield. They also had another toy model along the way. C equals 1/2. C equals 1. Kappa equals 8 is a uniform spanning tree. Now, it may not be obvious how you can get a spanning tree out of this, But if I take a discrete spanning tree in Z2, I can do a random walk that goes around this little steps. And if you think about this, it's going to be a space filling guy. And this is also C equals minus 2. And these two are related. And the relationship between the two of them relates to what Yves Lejean talked about yesterday about the relationship between loop race walks and spanning trees. There's also cap equals 16/3, but which is FK using, but I won't bother to write that in. Okay, it's getting close to the time, so I think this is probably a good place to start. I mean, this is just the beginning of a, you know, it would take, if I really wanted a course in SLE, it would take 30 hours. So what you got was an hour and a half version of this, but I think I'll stop there.